I'm back. Apparently, there's a 15 time limit on this free recorder, but I believe this is where I left off. So just these two reminders, and definitely remember that the electrons are being removed from the outside inwards. So how you would tell is or how you would tell whether you've got an outside, or which one the most outside electron is, you need to compare the energy levels. The higher the energy level, the more outside it is. So if you're looking at an electron configuration, you just want to look for the highest number, and that will tell you that's the outermost electron for that. So let's take a look at this spectrum, and then I'll walk over how we can figure out a spectrum. So if you were presented with this, what you want to remember is that your outermost electrons are here. These are the electrons that require the least amount of energy, and then you've got your core electrons here. And again, notice that break. It's a huge difference from 104 to 6.84. Too much to put on a graph, so they just kind of truncate it or make it shorter. So this tells you that this innermost peak would be our 1s orbital. So again, because we were able to fill in orbitals after the 1s orbital, then this orbital must be maxed out with 2 electrons. So essentially what you want to do is you want to pick your outermost electrons, and you know to look back, find your 1s orbital, because you know that one has to be filled before any other orbital could be filled with electrons. So you now know the height of what 2 electrons will look like. So past that, we know after the 1s orbital, we get to the 2s orbital. Again, these two peak heights are the same, or you can also think that, hey, if we've already managed to fill orbitals past this one, then this orbital must be also maxed out with 2 electrons as well. After the 2s orbital, you have the 2p orbitals. You'll notice that the peaks are 3 times as high. You want to be careful here and do a really good accurate measurement. You definitely don't want to confuse it for like twice as high and end up with the 2p4. But it's 3 times as high, so that tells you that there's 3 times more electrons, so there's going to be 6 electrons. And now we get to our outermost orbital, so this is now our valence shell. Okay, this valence shell happens to have only a 3s orbital with 1 electron in it. We know it's 1 electron because this is looking like it's half the height of this one, so we know there's 1 electron in that orbital. So now we know this orbital, this element with 11 electrons is sodium. There's its full unabbreviated electron configuration. If you want to abbreviate, you could look right before sodium with 10 electrons and protons. That gives us a noble gas of neon. So put neon in brackets and then put in that valence electron. Again, these are going to be your core electrons. These are going to be your outermost electrons, or your valence electrons. Okay, they're not outermost valence, outermost or valence electrons. So this is how you would determine what element you've got. Okay, so we skipped this question in class. What if we used a photon of light that did not have enough sufficient energy to eject all the electrons? If you think about the electrons that get ejected, you always start off with by ejecting your outermost electrons. Okay, so I'm going to make this a 2p3, right? So these require less energy than this one. This is a core electron, so it's going to require a lot more energy. If you don't use enough energy in that photon of light, you will start removing the outermost electrons, but you might not get to the inner. Okay, so it might not be enough. It all depends on how much. But here, you might get a photoelectron spectroscopy, a PS diagram, where the 1s electron never got removed, so it's gone. So you could end up construing a 2s orbital as a 1s orbital. So you can actually mix up the elements if not enough energy is used in that photon of light. So what's going to get left off, it's going to be your core electrons. The more energy it takes, the more likely it is to be left off of that PES diagram, okay? So the last thing that we talked about was the Coulomb's law. Coulomb's law shows up a lot. When we talk about ionic compounds, Coulomb's law will show up. But essentially what Coulomb's law does is it talks about the strength of attraction between two oppositely charged particles. So this is strength of attraction. And when you talk about Coulomb's law, you don't ever just want to stop at, oh, stronger or weaker attraction. You always want to tell us what it's between two opposite charges. Okay? And Coulomb's law, or the strength of attraction between two opposite charges, Coulomb law states that it is directly related to the magnitude of the charges. Direct relationship means if the charges get bigger, so does the attraction between the two charges. If the charges get smaller, so does the attraction between the two opposite charges. So it's a direct relationship. So Q1 doesn't matter which Q and Q2 is, but one represents protons, one represents electrons. So this is magnitude, which means amount, how much. Okay, so this is a direct relationship. If this one gets bigger, this one gets bigger. On the other hand, it is inversely related to distance. So inversely related means the larger this gets, the smaller this gets, or the smaller this gets, the larger the attraction between the two charges. And that makes total sense. If you think about two magnets that are far apart, they're not going to attract each other at all. Or if two magnets are right next to each other, they're going to snap together super quick. The same thing works with opposite charges. Okay, if two opposite charges are far apart, there's no attraction there. But if as they start to get closer, that attraction will build between the two ions, and eventually it's going to be so strong it's going to pull the two together. Okay, so one thing I want you to notice is every time I talk about the attraction, I always tack on the words between the two charges at the end. You have to say that. It's just not attraction to anything. It's attraction between the two opposite charges. Okay, so keep in mind that when we ionize things, you have to overcome that nuclear charge. So essentially what that's saying is you have the protons in the nucleus attracting the electrons outside of the nucleus, and you have to be able to break that attraction in order for electrons to ionize. So this is some of the dialogue that I said between, or sorry, not between, I just saw the word between. This is some of the dialogue that I said regarding Coulomb's law, all right? And so this is the distance between the two charges, and it's inversely proportional. And so using this principle, we can start to look at how two PES of two different elements would be different. Okay, so instead of going back to the previous slide, I added a new slide. So I'm just going to go forward to that one. So here's sodium again, right? And so sodium has 11 protons and 11 electrons. Magnesium, 12 protons, 12 electrons. Here's its configuration real quick. Okay, 3s2. It adds up to 12 electrons. Here's our 1s2. This is a very high energy, two electrons that need very high energy to be removed. So here's our valence electrons out here. Okay, so two things are going to change. Obviously, the height of that last peak will be different because it is not a 3s2. It is not a 3s1, it is a 3s2. So the height of the last peak will be different, and also the position of the peaks will be different due to a greater magnitude of charges attracting each other, which means the attraction between your nucleus and your electrons are going to be stronger, which means you're going to have more or you need more ionization energy in order to remove the electrons. Okay, so to sum up, the last peak will be different, and we're going to go over how it's different, and then the position of the peaks, or the location, is also different. Okay. So we're going to explain, we have to explain how it's different. So one of the things in the AP test or whenever, even in this class, you never just want to end with it's different. You have to say how it's different. Okay. So for magnesium, we're going to deal with the position of the peaks. So because magnesium has a greater magnitude of charges, more protons and more electrons attracting each other, the attraction between the nucleus and the electrons will be stronger, which means it will take more energy to ionize those electrons. So all of the peaks will shift left. That's higher. Okay, so remember, this is opposite from what we're used to. So you're going to draw the peaks as similar as you can in terms of height, because remember, it's the same number of electrons. So the red I'm going to do in magnesium. This blue is going to be silver. I haven't figured out how to change the pen color yet. So these red peaks are going to be for magnesium, okay? So we shift the peak to the left to represent higher ionization energy. We kept the peak height the same to represent that they both have 1s2 as that first part of the electron configuration. So again, here's our 2s2 for magnesium. I'm going to keep that peak the same height as best as I can, but I'm going to shift it to the left because those electrons are going to require more energy to be removed. Okay, same thing for this one. Best as I can, same height, but I'm going to shift it a little bit to the left to symbolize higher ionization energy required. So now we've reached our last peak, so this will be different. This one goes back to the height for 2 electrons, so I'm going to do my best to match it with the height of these. This is R3S2, okay? So this is the difference between sodium and magnesium. The last peak is different, peak shift to the left due to higher ionization energy required. You guys want to be careful when you shift these. Look at, you notice when I shift these, it's only slightly to the left because all they've managed are, the only difference is 1 proton and 1 electron. So it's not going to be a huge difference in energy required. So it's a little shift to the left. You're not going to shove them way over to the left, okay? Little shift to the left. I think that takes us to the last slide. So hopefully this was a lot better than what you went through in class and you got a lot more information down. If you have any questions, you guys know you can always email me to ask for extra help. Okay, thanks. Bye-bye.